Hello, welcome to this video called Introduction to Turbulence. I'm François Schmidt. I'm a research professor at CNRS in Vimereux, France. This short video is done in the framework of the graduate school IFSI, which is Graduate School for Marine, Fisheries and Seafood Sciences. So turbulence is known from art. Here I showed some examples from the art, like this one from Da Vinci. Also, you have this painting or this one by Van Gogh. It's also known in the common language for turbulent kids or for turbulent crowds. A short video belongs to a series of 7 video capsules that will be recorded. And you have here the different topics. So here it will be the first topic about introduction to turbulence. So in physics, turbulence belongs to the field of fluid mechanics. So the general properties of turbulence is to have huge fluctuations. It's unpredictable. There is chaos. There is mixing. It's universal in nature. You can see, you can find turbulence for clouds, for the atmosphere, for the ocean, also in stars and in rivers, and also in engineering, for example, for planes, for renewable energy, and also for chemical reactions. So turbulence needs also to have injection of energy, then the energy goes from large scale to small scales, and at the end, if you don't inject energy, then everything stops. And at small scale, energy is dissipated into heat. You also have thermal convection, so it's another turbulent mechanism where turbulence is generated by a temperature difference. So if when you are cooking, for example, you have hot water below and cold water at the top, and because they have a different density, you have some movement that is generated, and after if you are above a given threshold, then you have instabilities and then you generate turbulence. So turbulence belongs to classical physics, which is a subdomain of fluid mechanics. The equations are known now for 200 years. They are called Navier-Stokes equation. It's come from Claude Navier and George Stokes, and it's valid for all fluids, for liquid and also for gas. So the scales, here you can see that the fluid mechanics includes viscous fluid and also turbulence. And there is a given scale, which is Kolmogorov scales, which marks the separation between viscosity and turbulence, and the order of magnitude is the millimeter. So where does it come from, Navier-Stokes equation? Navier-Stokes equation come from Newton's law, the famous Newton's law, where you can write the resulting force equal the mass times the acceleration. This is written for a virtual element of fluid of small size, and by applying different hypotheses, and we obtain a differential equation, which is the Navier-Stokes equation. It's a complicated equation. So in fact, you have nonlinearity. It's also a very complex systems because you have a huge number of degrees of freedom. So in fact, it's not solved up to now mathematically. And in fact, the Clay Mathematical Institute has proposed now 25 years ago some millennium problems. There are 7 mathematical problems that are proposed, and there is a prize of $1 million for solving every of these problems. Only one has been solved up to now, which is the Poincaré conjecture. And Navier-Stokes equation is a third of the problem. And you can see here, it's unsolved. So what are other properties of Navier-Stokes equations? They are deterministic, so there is no randomness inside the equation. It means that, in fact, if we know the present situation and also the past, then the future is unique. There is only one future. So another properties of turbulence is chaos. So the Navier-Stokes equations are deterministic. There is no randomness in the equation. So it means that if we know the past and the present, then there is only one future. But in fact, they are chaotic. The word chaos was introduced in the field of fluid mechanics. It means sensitive dependence to initial condition. So as we can see here, you have if you have two trajectories that are initially very close, in fact you have exponential divergence of the trajectories. That's the meaning of the word chaos. You have randomness, so it means that in fact even if there is no randomness inside the equation, the solutions are irregular. They seem irregular. They have a random aspect. Here you can see a graph showing high frequency measurement of the velocity of the atmosphere at a given point, and we can see that it's really irregular. It has a random appearance. And so it means that, in fact, we need to use the theory of probability and statistical methods to study turbulence. So it's a typical complex system. So it means that we have a nonlinear equation. We have coupling between different components. We have a large spatial scale range and large temporal scale range and very large degrees of freedom. And so we have three, in the geosciences, we have three approach. So one is theories and models. The other one is observations. It means in situ measurements. And the last one is experiments in the laboratory. And so the next topics will be about these three categories of works in turbulence. So observation, modeling, and experiments. So that are my books and recent publication about this topic, and I thank you for your attention.